Good afternoon, everyone. It is time for us to begin our webinar today on 802.11ac frames, what's changed. And this is going to be a brief overview of the changes in 802.11ac frames without going into extensive depth into every detail of all the bits and bytes. The goal here is to get an understanding of some of the things that have been introduced with 802.11ac and how they're going to impact our thinking about frames and frame analysis when it comes to troubleshooting wireless networks. Now, there are two ways to think about frames for either wired or wireless networks. We can think about frames from the perspective of the designer of drivers and chipsets that need to worry about transmitting frames. And we can think of them from the perspective of network implementers, troubleshooters, and optimizers who need to look at frames in order to see what's going on the network, how the network is behaving, what they can do to make it perform better, and so forth. Well, that's primarily our focus at CWNP. So our focus at CWNP is not on training programmers who are going to develop chipsets and drivers. Our focus is on training and certifying those who actually do have the ability to implement wireless networks and troubleshoot them. So today we're looking at the 802.11ac frames, and we're going to talk a little bit about what's new in them. Now, the first thing though is to let you know a little bit about what CWNP offers for those of you that might be with us today who are not familiar with CWNP in detail. And just in case you have any difficulty seeing what's on the screen, this is a slide-based presentation, so you should see the slides and be able to hear the audio as well. Now, the CWNP certifications include CWNA, which is our flagship certification. We have more people certified as CWNA than any other level. And then we have professional level certifications like CWSP, CWDP, and CWAP. And CWAP in particular is very heavily focused on understanding 802.11 frames and how to analyze them from a troubleshooting and performance perspective. CWSP is about security and CWDP is about design. And these are our three professional level certifications. Now, an individual who gains the four certifications I've just mentioned, CWNA, CWSP, CWDP, and CWAP, can then apply to become a CWNE. There are specific qualifications for that, and you'll certainly want to check out the CWNP.com website to read about the CWNE requirements, because it's not just about taking a test. For CWNE, you have to have the four certifications previously mentioned and experience and other qualifying factors. So you want to make sure that you check on the specific requirements at the CWNP.com website. So the agenda today then is to talk, first of all, just briefly about 802.11 frames, the standard frame format, and then to go into a little more detail about the changes at the MAC layer and the PHY layer. So when we deal with framing with any kind of networking, we are dealing with MAC layer frames. This is all about the bits that format the thing that should be sent on the physical media. Whether that's a wire or RF waves, it's still needing to be formatted before it's passed on to the physical layer, which is going to then also add some extra bits for the transmission at the physical layer. Some of those bits are simply for the purpose of training the receiver when it comes to wireless, so that the receiver knows that a frame is coming in and it can start listening appropriately for it. And some of the bits actually say something about the payload, like the size of the payload, so that the receivers can understand how long it's going to take for that transmission to take place. So we'll talk about these as we go along. Now, the presentation today is going to be somewhere around 20 to 25 minutes. It's going to be a shorter presentation, not an extremely long one, because again, we're not going into great detail, just getting you started in thinking about the new things in 802.11ac frames. So before we get into any of the content, let me recommend a couple of things. First of all, if you want more information on frame analysis for 802.11, a really great source is the different protocol analyzer vendors. So for example, you can look at Tamosoft's website, Air Magnet Wi-Fi Analyzer Pro, OmniPeak is another good wireless analyzer program. All of these are applications that are specifically designed for analysis with 802.11. And their websites, but also the help within these applications is very useful. And you can download trial versions of the applications to see that information. So that's a good source. Another is we are in the process of editing right now a brief series of blog posts that'll give you an overview of some of the information I mentioned here today, but also more information as well. And this will be authored by a guest blogger, and you'll get to see those coming up at the CWNP blog pretty soon. So that would be another source as well. And of course, the ultimate source for all things 802.11 analysis is the CWAP certification. And so if you really want to go into depth to all of this information about frames, then the study guides for the certification, the practice exams, and of course, gaining that knowledge to pass the certification itself. Now let's talk a little bit about then this process of encapsulation. Because when we talk about frames, what we're talking about is the container that holds useful data. When we're dealing with useful data, we're dealing with layer 3 and above. Technically, we're dealing with layer 4 and above, but we can call it useful data at layer 3 and above because it's going to some destination outside of our local area network in many cases. It has an IP header, it may be going to the internet, it may be going somewhere on our wide area network, it may just be going on the local area network, but the point is, at that level, layer 3, it has an IP header, and from that point up, we're dealing with something that we can transfer through our network or even out of our network. So lower layers, the data link layer and the physical layer, are really what define the different kinds of networks that we use, whether that's Wi-Fi or Ethernet or some other layer 1 and layer 2 technology. With 802.11, of course, we're dealing with the MAC header and MAC footer or frame check sequence to be able to do integrity checks against the data. So all we do is at layer 2, particularly at the sub-layer of layer 2 called the data link layer, we actually, or the MAC sub-layer of the data link layer, we actually encapsulate the upper layer information. So the IP header, the TCP UDP header, the data. We take all of that, we wrap it inside of the 802.11 MAC frame format. So the actual upper layer information becomes the payload of the MAC frame. This payload is stored in the section of the MAC frame that actually has a very specific name. And that name is simply going to be the frame body. So the frame body is the data. It's the thing the frame is delivering, okay? Think about it like this. If you have a window in your house and there's a frame around that window, you didn't put it there for the frame. You put it there for the window. The window is what you want. You need the frame to hold the window, but you actually want the window, not the frame. Okay, well, maybe you have a fancy frame, so you like the frame too, but you get the point. The point is that we have the frame to hold the window. We have a picture frame to hold a picture. The point is then we have a frame to hold the upper layer useful data. It's just used to hold it until it gets to the next point where it doesn't have to hold it anymore. And then if there are many hops, there might be many devices that create frames to hold that upper layer data along the way until it gets to its destination. Now we'll talk a little bit more about what's in this frame in just a moment. But in addition to the MAC layer, it is important to know that there is encapsulation at the PHY layer. Now, technically speaking, encapsulation, you would think of it as having a header and a footer. Well, the PHY layer sort of has a footer in that there are some extra bits sent after the data in order to communicate to a convolution coder that the frame is done. But the point is that we mostly focus on the PHY header, the information that is at the front of the payload before the MAC frame. And so we'll talk a little bit about what's changed in that area as well in 802.11ac. Now, first of all, I want to back up for just a moment and point out a big change that came in 802.11n. In 802.11n, we were introduced to frame aggregation. Now, to understand frame aggregation, there are a couple of terms you need to understand. These terms are MSDU and MPDU. An MSDU is a MAC Service Protocol Data Unit, a MAC Service Data Unit to keep it nice and short. The point is that it is the chunk of information, the bits, the ones and zeros, that the MAC layer needs to process. It's received from the upper layers, or it could be that it's transmitted back to the upper layers when a frame is received. When a frame is being transmitted, the data comes down through the upper layers. The MAC layer receives the IP header, TCP UDP header of the data. It then treats that information, the stuff that came from above, as the MSDU. It needs to take the MSDU, put a header and a footer on it. After it has appended a header and footer, it is now called an MPDU, a MAC protocol data unit, and is ready to be sent down to the physical layer. Okay, so an MSDU, a MAC service data unit, received from the upper layers. After the MAC header and footer are added, it becomes an MPDU and it's sent down to the lower layers. Well, what 802.11n added was the ability to actually aggregate multiple MSDUs so that we can send multiple MSDUs in a single MPDU. And notice the way the graphic represents it here. We have 3 IP headers, 3 TCP or UDP headers, and 3 data payloads. They are embedded within one MAC header and MAC footer, or frame check sequence. So the point is that we're dealing here with multiple MSDUs. This was an added feature in 11n to get more data through more quickly during a transmit opportunity. The MPDU, remember, is what comes out of the MAC layer. Well, 11n also introduced the aggregated MPDU. In this case, what we're doing is we're taking entire MAC frames, multiple MAC frames, and sending them in a burst at the physical layer. So notice that we have not just 3 IP headers, but we have 3 MAC headers, and we have 3 MAC frame check sequences. And so the point is that we're actually transmitting all of that extra information together at the physical layer. So for now, I just want to point out that this was introduced in 11n, the ability to aggregate at the MSDU or MPDU level, and this gave us the ability to send more data more quickly with higher data rate clients, 802.11n clients specifically then. And now we have support for aggregation of frames with 802.11ac as well, but something really important has changed. With 802.11ac, all frames are sent as aggregated MPDUs. That is to say, even if we're only sending one frame, we have one MAC header, one MAC frame check sequence, one MAC frame, we're still sending it using the PHY format for an A-MPDU. Okay, so that was a decision that was made for efficiency purposes, and it's simply because there are very, very high data rates that we have in 802.11ac. And to keep the discussion simple today, just know that by doing it this way, by always sending aggregated MPDUs instead of only doing it when we need to, we end up getting more efficiency in our overall communications across the board. Now, don't be alarmed. That doesn't mean an 802.11ac device cannot communicate with an 802.11a device. It can. It's simply going to communicate in such a way that it's a standard MPDU or a standard PHY communication with OFDM, right? So it's backward compatible. It knows it's talking to that device. It'll talk to it in a way that it can hear it and understand it. But when an 802.11ac device is talking to an 802.11ac device, it's always going to be an aggregated MPDU in the transmission. Now let's talk then a little bit about the standard 802.11 frame. 802.11ac does redefine the general frame format. The general frame format is just what it sounds like. It's the frame that's generally used. It's the frame that's most commonly used. There are variants to the format. There are different frames that include things that are not listed here, and there are frames that do not include some things. So there are different frames, but the common frame format, particularly used for all data transmission, is the one we see here. Now, one thing you would notice immediately if you had looked at the frame format for 11n and 11a, which is all we care about with 11ac, by the way. Remember, 11ac works in 5 gigahertz, and that's all. It doesn't work in 2.4 gigahertz. So we're not really worried about what a frame might look like down there, are we? We're focused on frames that an 11ac device would send and that other devices that are not 11ac might be able to see. For example, 11a and 11n. So the early frame bits are effectively backward compatible. because we still have a frame control field, we still have a duration ID field, and so forth. But there are frame bits later on, like the HT control field can be of the VHT variant, and it will mean that it has some stuff in it that older client stations would not understand. Now, an important thing to note is the frame body size was changed with the release of 11AC to, instead of being 0 to some maximum, simply stated to be variable. And the reason it's stated to be variable is there are several different factors that can impact the actual frame body size. But the maximum for the MSDU frame body size is 11,454. So it's bigger than it was before. 11N maxed out at 7,955 with aggregated MSDUs. 11A was the old 2,304 bytes. These are, by the way, bytes or octets if you prefer to be more specific. An octet is an 8-bit byte. Okay, so a byte could be something other than 8 bits, and that's why for better accuracy, it's good to say octet, but many people always think a byte is 8 bits. Well, if you think that, you're right in this case. So the frame control field is 2 octets or 2 bytes, which means it's 16 bits, right? For example, HT control field is 4 octets or 4 bytes, which means it's 32 bits, okay? And so what does that mean? Well, each one of those ones and zeros can mean something, right? So if you've got 16 bits in the frame control field, you could potentially represent 16 different things that can be either on or off, yes or no, up or down, in or out. In other words, it's a binary toggle, right? Or you could use 2 of the bits to represent something, 3 of the bits to represent something, and so forth. Well, in the 802.11 standard, all of these individual fields are defined. Some of them, it is just 1 bit that represents something. It's a yes or no type thing. And some of them, it's multiple bits that represent something. But you can look through the standard, which is freely available for download at the IEEE website. If you do a search for Get 802, you'll find the project where you can download these standards. And when you download them, you can scroll through, do a search for general frame format, and you'll find the beginning of the frame discussions there, and then you can go through and see what each bit represents. Many people are overwhelmed sometimes when they start looking at frames and they look at individual bits and they think, how could I really be expected to understand all of these ones and zeros? Well, you're not really expected to be able to look at, say, 16 ones and zeros in a row, like the frame control field, and just immediately in a glance look at it and say, okay, I know everything about the frame control field. You would instead, as a human being, look at a reference and see what the first bit represents and what the second bit represents, what the third bit represents, what it means if it's a 1 or a 0, and so forth. Okay, so you would actually look at them bit by bit to process it, because we don't normally as humans speak the binary bit-based language, do we? We're not computers. A computer, on the other hand, can process them extremely rapidly and figure out what they mean, what they represent, and then do the appropriate thing. So it's not hard to understand frames, it's just time consuming, okay? Because it's simple to know, okay, these bits mean one of these several things. Now, it can get challenging when, for example, you might find out that a particular bit is telling you that something is being used like space-time block coding, okay? So it's saying, yes, we are using space-time block coding, and you think, oh, I don't even know what that is. And then you've got to dig around in the standard or otherwise to find out what it means, because sometimes the 802.11 standard uses a technology and it simply points out that it's using that technology. It doesn't always define the details of how it works. It's assumed you would be able to find that elsewhere. Or it may reference another standard where you could find it. And so the point is that it may seem like it's hard, but it's actually just time consuming because you've got to dig up the information to get what you need. That's why, when we can, we want to use a protocol analyzer that's 802.11 intelligent. It understands what these bits mean, and then it represents them to us in a meaningful and useful way, so we don't have to look at a bunch of ones and zeros and try to figure things out. Now, one of the things that's obviously going to be added, if you're familiar with frame analysis in 802.11n, is VHT Capabilities Information. So the VHT Capabilities Info, or just Element, it's called both things. It's called the VHT Capabilities Information Element, and it's also called the VHT Capabilities Element within the standard. Mostly within graphics, you'll see the word info or information, and then within text, you'll see Capabilities Element. The concept is that this chunk of bits, which as you can see here is 14 octets long, 1 for the element ID, 1 for the length, 4 for the VHT capabilities info, and then 8 for supported MCS data rates. So the point is then that what this is going to tell us, this chunk of information, is important things like the maximum MPDU size, the supported channel widths. Is it 20, 40, 80, 160? Are you using a short guard interval? There's a typo in the slide there. It should be GI, not GIU. Are you using a short guard interval when you're dealing with 80, 160, or 80 plus 80 channels? Or are you using the long guard interval in such case? What about the single user beamforming capabilities? So this will communicate whether or not the station is capable of sending or receiving single user beamforming and multi-user beamforming. All of that's included in this. And then the VHT TXOP power save support, whether that is going to be supported or not. It's a new power save feature in 802.11ac that has been added. This is part of what is included in the VHT capabilities information element. Now this is going to be in beacon frames and probe request and probe response frames, for example. So this is not necessarily something you're looking for in a data frame. This is something you're looking for in frames that communicate to devices what the network is capable of so they can decide whether or not to participate in that network. Now, in addition to the MAC layer framing, it's important to know, as I said, there is PHY layer framing. And I'm not going to go into tremendous detail about PHY framing today because it can get really complicated, but let me give you the high-level overview of what's going on here. First of all, on the far right, you see the data. Well, the data, as you can see, is simply stated as being data. And it says the data field carries the PSDU. Well, the PSDU is the PHY service data unit. Now, you've heard something similar to that already today. You heard about the MAC service data unit, right? Well, the PHY service data unit is the MPDU that is received from the MAC layer for processing by the physical layer. What processing does the physical layer do? It adds the LSTF, LLTF, LSIG, VHT SIG-A, VHT STF, VHT LTF, VHT SIG-B. It adds those things that are prepended before the data in the graphic here. And this graphic, by the way, comes right out of the 802.11ac standard. You'll notice that this represents, instead of octets, it represents microseconds. Okay, so it's telling you there's a short training field for 8 microseconds, a long training field for 8, then there's a non-HT signal field for 4 microseconds. Those first 3 fields are backward compatible all the way to 802.11a, which is all that matters in 5 gigahertz. Remember, we don't care about 802.11 prime in 5 gigahertz. The old frequency hopping spread spectrum and direct sequence spread spectrum, they don't matter to us in 5 gigahertz because 5 gigahertz was first introduced with OFDM with 802.11a. And then we had HT with 802.11n and now VHT with 802.11ac. And eventually with 802.11ax, we'll have more. So the point is that what we have to deal with for now is backward compatibility. We need something to tell everybody listening on the medium there's a frame about to be transmitted, and that's what the non-HT short and long training field and signal fields do. They get that information out there. The VHT signal A field is giving some specific information about this particular PHY communication. It is something that only a VHT station would be able to fully understand properly. The VHT short training field is a training field that, again, only VHT would understand, as well as the long training field. Getting ready and leading up to the signal B field, which is the one that's going to have some information about the length of the actual data to be delivered. And then finally, we get our data field. Now, the data field does have prepended to it some communications that are used in order to synchronize for convolution coding and things like that. But generally speaking, it's just the PSDU. It's the upper layer information that came from the MAC layer and is now being sent by the PHY layer. So here's the thing, with 802.11n, we had a legacy PHY framing format, and then we had an HT framing format. With 11AC, we just do away with that. This is the one PHY framing format that we use so that we're able to communicate backwardly as well as with the newer standards. Now again, this is talking about when we're implementing this, communicating with an intended frame for another 11AC device. The question was, what are the VHT training fields the same as the HT training fields? And the answer is that they are not identical. They are now specific for VHT. You can get more information about the details on that in Matthew Gast's book. If you have a copy of that, 802.11ac, A Survival Guide, he does good in that. If you don't want to go to the standard and have to read it there directly. But there is information in the standard on that as well. Okay, so now let's wrap up the webinar today to talk about, well, how do we get these frames? Because we really don't want to just look at a bunch of ones and zeros, right? Well, you can capture 802.11ac in a few ways. ComView for Wi-Fi, OmniPeak, and Wi-Fi Analyzer Pro can all capture 802.11ac. ComView for Wi-Fi can do it with a USB adapter. Right now there are 2x2 11AC adapters that you can use and capture with ComView for Wi-Fi. It works great, and if you're just wanting to do it in the lab in order to see it and capture the frames and understand them, then 2x2 is all you need. The problem is in the real world we have those MacBook Pros out there, we have other 3x3 devices like access points, and so we need to be able to capture those. Well, you can do that with AP capture, which will work with ComView for Wi-Fi. It also works with OmniPeak and Wi-Fi Analyzer Pro. So you can do AP capture for those. Now, Wi-Fi Analyzer Pro from Air Magnet does also offer a custom adapter that you can get. It's actually an express card adapter. And so you would need a laptop with an express card slot, you know, like a Lenovo laptop or one of those, because not too many of them have them anymore. But you would need one with an express card slot, and then you can use that custom adapter, which is a 3x3x3 11AC adapter. So you'll be able to capture everything from 3x3 11AC all the way back to 11A. So those are some ways. You can use a MacBook Pro to do your captures, and that'll allow you to capture 3x3x3. And of course, you can just use APs. In other words, you can capture on the AP, and then you can just open your capture file for analysis. And I've mentioned this AP in several webinars over the past year or so, and it's the Cisco WAP371. It's inexpensive. You can get it for under $300 US. If you search around Newegg and places like that, usually. I'm saying you can. I haven't looked today to verify that it's still out there and available at that price, but the Cisco WAP371 is an inexpensive, made for small business AP, but it has built into it the ability to do protocol capture. So you can capture the frames 3x3x3 and then analyze them. Now, of course, we're right on the cusp of seeing 4x4 APs in the enterprise with 11AC, and then we'll have to figure that out again. But for now, this is what we're looking at. And then when it comes to analyzing it, obviously we can use ComView for Wi-Fi, OmniPeak, Wi-Fi Analyzer Pro, and you can also use Wireshark. Wireshark does have decodes for 802.11ac. It's just hard to capture directly in Wireshark for 11ac. There really haven't been any major updates to capturing within Wireshark itself since early 11n. And even with that, we can do it in Linux. So we can use Linux, we can capture with 11n adapters, we can look at it in Wireshark. But even then, there are some real challenges with some adapters to being able to capture 40 megahertz 11n channels, much less 11ac capture capability, which we're really not seeing yet on the Linux platform. So that's going to be something to watch for as it comes along. But for now, the momentum really is moving into the APs and doing the protocol capture there. And when you need to capture from the client side, you want to see what frames look at where the client is. Again, you have the option of only having 2x2 capture with ComView for Wi-Fi and a USB adapter, getting an Express Card laptop, so you can use Wi-Fi Analyzer Pro with their Express Card adapter, or you can take your Cisco WAP371 with you and your PoE switch, get a little mini PoE switch you can carry with you, and go to the location, plug it in, and do your capture. It's not pretty, but it does get the job done, and it will work to do capturing at the client location rather easily, actually. Okay, Well, that's what we wanted to cover today, to give you an overview of the new features and capabilities in 11AC frames. We'll begin to explore these more and more as we look at later webinars. We're in the process of updating our CWAP curriculum right now and getting ready for a launch of a new version of that exam next year. So you'll see more webinars coming, giving even more detail on these topics as we move along. Also, a quick note before we open up for any questions you might have. The Wi-Fi Trek Conference is literally next week. So it's coming up right around the corner now. And we're going to be excited to be in San Francisco. So if you haven't heard about it, looked into it, make sure you check out the website. The URL listed here is cwnp.com/2015 National Conference. And it is not too late to attend. You can even register at the conference and walk in and attend. That is a possibility that you can do. If you have questions, contact customer care at cwnp.com. If you have questions about the webinar today, do feel free to type those in. You can either just type them into chat and send it to all participants, or you can type it into Q&A and I'll try to get to them there as well. Okay. Will the presentation be posted online? Yes, we will be putting this on our YouTube channel at CWNP TV. So do a search for CWNP TV on the YouTube channel and or on YouTube, and you will be able to find it there. Okay. Any other questions you might have, feel free to go ahead and send those in. I'll get them to you as quickly as I can. Beacon frames have both HT info element and VHT info element on 5 gigahertz. Question: that is correct. And so they do have both of those in the Beacon frame to communicate HT capabilities, because all 802.11ac devices are automatically by default 802.11n capable as well. So they will communicate the HT capabilities as well within the Beacon frames. That is correct. Okay. Give you a moment here if there are any other questions. If you don't have questions and you need to run, feel free to go ahead and go now. But I'll hang out for just another minute or two to see if there are any other questions to come in. And let me say thank you for attending, for those of you that have been with us today. Okay, I'm not seeing more questions coming in. So at this point, I'm going to go ahead and wrap up the webinar. Thank you very much for attending. And again, if you do ever have questions in the future, you want to talk to somebody, our forums are a great place to get involved. If you go to cwnp.com, go to the forums there. There are people that will help get your questions answered. It's a great community to get support when you're trying to understand 802.11. So make sure you take advantage of that. And for those of you that will be at the conference, I look forward to seeing you next week. Have a great day.